this open floor. Any questions that you have, go ahead and ask. Hey, you're tongue-tied. Well, Ken, did you want to follow up on your question, or are you okay with that?
Can you explain it here, please?
All right. So which one is that?
7524.
Okay. Okay. All right, here. All right, so let's see. 7524. All right, let's do this. So I'm going to copy it to my OneNote. Okay. All right. Oh, this is in the wrong place. Sorry. I didn't mean to put it there. Let's drag it down. Oh, let me delete it and do it again. Sorry. Do it one more time. Okay, here we are. All right. So here's the exercise. It says in the above proof that trace AB equals trace BA, we assume that both A and B were square matrices. So the formula is still true when A is m by n and B is n by m. Okay. All right. Well, let's look back at the above proof first before we start this. So the proof says, all right, so here you're trying to show that trace of AB equals trace of BA. All right, now, so the way the proof goes is like this. The trace of AB is the sum of the diagonal entries, and the diagonal entries are the ones where the row index and the column index are the same. So that's why you have this sum over II here. Sorry, just made it bigger so you could see it, but now I lost it. All right, let's go here. All right, here we go. Yeah, so here you see the diagonal entries have this form, sum AII. All right, so let's look at this proof here. Here you have the sum of diagonal is AII. So here you have now, but you need what AB is. You need AB, the ith entry of AB, and this is the expression that was before. There's an expression for ABMN. When you take the product of two matrices and the first index is M and the second index is N, then you have this formula. And here we just replaced M and N with I and I. All right, now because the I and the K, because you're summing over all I and all K, the order of summation really doesn't matter. If you made a dot diagram of this, it would be a rectangle. Actually, it's a little bit because we didn't put the limits here. Let's go ahead and put the limits in. So I'm going to copy that here. Where are we here? Okay. All right, so first I'm going to say, we'll say suppose. Let's put some sizes in here. Now here it says that A, here it says that A is a m by n and B is a n by m, right? A is m by n, so that's m rows and n columns, and B is n by m. All right. All right. So in that case, what are the dimensions of these sums? I runs from 1 to what, and K runs from 1 to what? That's the question. When I multiply A and B together, when I multiply the A and B matrices together, what values does K run between? All right, so that's at least that's a good guess. It's either M or N, right? So A looks like this, and B looks like this. Doesn't matter. I just made the N bigger than the M. It would work the same way if it were smaller. All right, so B looks like this. Now, when you take the matrix product, you take the rows of A, inner product with the columns of B. And since they're n entries in each row and n entries in each column of B, that's what Trey said, I think it was Trey anyway, was correct, that this is a sum up to n here. That's a sum up to n. All right. Now what about this I? This I is summing over the diagonal entries of AB. Now what size is AB? How many rows and how many columns? All right. In fact, this has the number of rows of AB is the number of rows of A, and the number of columns of AB is the number of columns of A. So this is M and this is M. So you can say it this way: if you have A times B equals AB, A is going to be here in M by N, and B is N by M. These two have to agree, and this M here is the number of rows of AB, and this M here is the number of columns of AB. All right, so AB is a square matrix that's M by M. So what does that tell me about the limits here? What limits here?
It runs from I equals 1 to M.
It is M. It is definitely M because these are diagonal entries. All right, so if it doesn't change here. Now if you notice, the limits of K don't depend on I, and the limits of I don't depend on K. So in fact, I can write them as a double sum like this. So I can say IK goes from 1 to M and N, like this. All right, now let's look at trace of BA. There's a formula for trace of BA as well. And go down here and see. Go back to the book. That would be this one here. All right, so let's do that. Let's make the copy. Insert, screen clipping, do this. And that was good. All right, now in this case, let's get the sums right. Okay, so here we have BA. So here we have B. B is N by M. And A is M by N. So that means BA, if I do the same thing I did up here, that means that these two have to agree. Those agree, which is good. And then this N here will be the number of rows of N, and then this N here is going to be the number of columns. So BA is an N by N matrix, not the same size. All right, so let's translate this information into finding out what are the limits of this on these sums. So the I here, in this case, what does I run between? In this case, this I is summing over the diagonal entries of BA. BA is a N by N matrix. All right, so this is I equals 1 to N. Okay, so I can make this I equals 1 to N. And then what about K?
K runs from 1 to M.
K runs from 1 to M. It's the other index. So here we have IK equals 1 to, and then I runs to N, and K runs to M, like this. All right, so let's compare these two expressions. Oh, wait. Oh, there's a mistake here. A big mistake. This should be AKI times BIK. I don't know where the BIK went. Sorry. Big mistake. I'll have to fix that. Right? That definitely needs to be there. All right, so we've got two expressions here. We've got this expression. We've got this expression here. And we want to compare this with the expression up here. The question is, are these two the same? All right, so this one says AIK BKI. This one says AKI BIK. Uh-oh, not the same. What's the problem?
You need to substitute the variables because the variables run the opposite. The variables represent the same thing, but they're in the opposite order, if you will.
Yeah. All right, so here we have, so let's write this one, some I and k, m and n. Then here I have AIK BKI. Now what I think so what you're saying, I think, is that I'll exchange the I and the K.
Yes.
And that doesn't change anything. Doesn't change the value. That's just changing letters. Doesn't change the value. All right? And that will give me, if I exchange the I and the K, I'm going to get some. In this case, it will be KI and MN. And this would be AKI BIK, which is exactly the same as this guy. So these are equal. Okay. All right. So this one is equal to this, and this one is equal to this. So they are all equal. So everybody's happy. And notice that here I did not assume that A and B are square. There's no assumption that A and B are square. So this proof works even if A and B are not square. Say it again.
Yes, this is in the OneNote. Right?
Sorry?
This is in their class OneNote?
Yes. Yes. This is in OneNote. In fact, all I have done really, if you come down to it, I've just repeated this proof. I haven't done anything different than what's contained in this proof in the text. I haven't done anything different. I just put in what the limits actually are. So there you have it. Okay, what's next? Well, I should go back. I had told you that in class here, I think it was this class. Was it this class? No, maybe the previous class. Let's see. I think I'm going to have to zoom out. No, not there. Maybe it's here. Oh, here we go. I did something with the deltas here. I never did finish this. Okay. So I never did finish this. So I did A and B, but I didn't do C and D. Now this is actually quite a this is a not easy problem. This is not an easy problem at all. And so if you remember, let me take you back to the problem. If you remember, the problem is that you have F and B, and Fij equals this funny stuff here, and Bij is this funny stuff here. All right. So actually, if you want to get an idea of what's going on, and you know how to matrix multiply, it might be a good idea just to write out what these matrices look like. So let's see what Fij looks like. Okay, so let's do this. So Fij is delta I plus 1j minus delta ij. So I'm going to do that down here. Why is it doing this to me? Oh, because what happened? Oh, there, okay. I think it went down too far. All right. All right, so we have Fij is equal to, I think it was delta I plus 1j minus delta ij. Let me check that. Okay. Let's see. Delta I plus 1j minus delta ij. All right, so let's see what that looks like. Okay. All right, so if I was going to write the matrix F, all right, now delta I plus 1j, well, first the delta ij, that's the same thing as the identity. This gives me the identity matrix. We talked about that before. This says that this delta is 1 when I equals j. So it's going to be 1 only on the diagonal entries and 0 everywhere else. So this delta ij is giving me minus 1s on the diagonal. I mean, together with this minus 1 here. And these diagonals go down. Now, what about this one? Well, let's just do some examples. Delta I plus 1j. All right, so here I have to understand what the delta means. Suppose I is 1. All right. Then if I is 1, then for what j is this non-zero? So I have when I equals 1, what I have is delta 2j. Now when is delta 2j non-zero? Remember the definition of delta. Delta, well, let me just say KL, that's equal to 1 if K equals L, and it's equal to 0 if K is unequal to L. Those are the two possibilities. So when I equals 1, here I would have delta 2j. When is this going to be non-zero?
When j is equal to 2.
In this case, the only j that makes this non-zero is j equal to 2. So that means row 1, column 2. There's a 1 here. All right. Now how about when I equals 2? I'm not sure where I'm going to write this. Here, what I can do, I suppose, is take this down. I'll take this and move it down a little bit. Should be good. Okay. All right, so here we get when I equals 2, then we'd have delta 3j. And that means that j is equal to 3. And then the same thing, if I equals 3, then you're going to get j equal 4, etc. So when I equals 2, j equals 3, where is that? Row 2, column 3. And then 3, 4, where's that? Right. All right. So I think you can see the pattern. You've got these ones. You've got this stair step of minus ones. Then you've got the stair step of ones, and everything else is a big fat zero. That's all zero here. That's all zero here. So that's what f is. F is going to look like that. All right. So let's think about what b looks like. So b was equal to, and I have to look back and see what it was. B was equal to delta ij minus delta I minus 1j. So this is equal to delta ij minus delta I minus 1j. Okay. All right. So if I'm going to write, so this actually should be bij. That's what that is. But if I'm getting the matrix B, all right, now let's use the same technique to do this one. What does the delta ij give me? What non-zero entries is that going to give me? Well, we did the same thing up here, right? We had a delta ij up here, and what did that give us? Let me do my cursor attention here. This one gave us the identity matrix. Right? This minus delta ij gave us all these minus ones on the diagonal. All right, so in this case, we're going to get ones on the diagonal. All right, and then so on. Now, what about this one? What is this going to give us?
It's going to give minus ones in every spot underneath the 1.
Yeah, that's very good. It's underneath now, because you can't have I equals 1 because that's 0. But if you had I equal 2, then you have j equal 1. And if you have I equal 3, then j equal 2, and so on. So here I have minus 1, minus 1, minus 1, etc. All right, and then I have big fat zeros below here and here. Okay. All right, so now we know what we're multiplying. So let's see what happens when we multiply f times b. So you can do this using matrix multiplication. If I take f times b, well, f is going to look like this: 1, minus 1, 1, minus 1, 1, minus 1, dot, 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 and zeros here, times, and then b is going to be 1, minus 1, 1, minus 1, 1, minus 1, dot, 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 like that. All right, so let's go for this. Okay, so now, whoops, sorry. Using matrix multiplication, what happens when I multiply the first row here times the first column there? I'm going to take the first row here times the first column here. What is that going to give me? Any ideas? You get 1 here times 1 here, plus negative 1 here times negative 1 here. So it's 1 plus 1 or 2. So in fact you do get 2 here. All right, now let's do the first row with the second column. What is that going to give us? Here I have a 0 here. There's this 1 times this 0 plus this minus 1 times this 1. And then these are zeros. and so on. So what do I get in total? I get a -1. All right. All right. And then how about if I go to the next column? I have zeros here. If I go down this column. Well, from here on, what you can see is that the first two entries are always 0. And it's always the first two entries here that multiply the first two entries here. So the rest of this is all 0. 0 all the way out. Let's go to the second row. Oops. Having trouble fitting everything here. What happens if I multiply the second row here times the first column? I get 0 times 1 plus 1 times -1 plus -1 times 0, etc. So what's the answer? You guys all having lunch? Or just all right. All right, well, what do you think? What's the answer if I multiply this row times this column?
It's a -1.
I'm getting a -1. How about this one here? What do you get? Okay. How about this one?
-1.
-1. Okay. What do you think the pattern's going to be? -1 both sides on both sides of the aisle, and zeros everywhere else. So how would you write that using the delta notation? First of all, the 2's on the diagonal, how would you write that using delta notation? Yes. So, but we know the way to get a 1 on when I equal to j is just delta ij. Okay. And then you need the -1 here and the -1 here. Well, look, this -1 here is in the same position as the -1s, as the ones were here, right? Same position. Where did these ones come from? That was this guy, right? The green ones came from this guy. So instead of adding delta I plus 1j, I have to subtract it. Okay, and then how about the -1s below? Well, those -1s below are in the same position as these guys, right? So where did these guys come from? That was in B. So where did these -1s come from? This guy. Okay, came from here. Right. So I have minus. Okay, so that's my final answer. All right, and then they also asked for BF. So you can try to do BF the same way. Now you can also do it directly with the indices, but maybe I should just show you one way. But you can actually do these indices directly. Whoops, what happened? Like I didn't finish the C and the D, but it turns out that the C and the D. So here you only get two terms, and it turns out that the C and the D work out to get you the other two terms. Now, did I screw up something? That's a little funny there. It looks like I got the signs reversed or something.
That's what I'm trying to figure out.
Delta I plus 1j. Oh. Well, no, that should be right. And then here we got, well, it should work out. Because it certainly seems backwards. Let's see. Oh yeah, there's certainly something wrong here. This is not a minus here. When you multiply the, no, it is a minus.
Yeah, can you work through it symbolically? Because that's the way I tried to do it when I
Okay.
first did it.
All right, sure.
I don't understand why I didn't get the same answer that you got.
All right, let me see why. Let me look at this. Maybe I did something wrong here, because something is screwed up here. This, that's a minus, and that's a plus. So, all right, so there's something I screwed up somewhere, I think. How could that be?
Wait,
How could, just give me a second to see if I can.
can you go all the way down to the left?
It looks like I must have gotten some signs wrong somewhere. I must have gotten some signs wrong somewhere, but I don't see quite where.
I think
Oh yeah, I think I can see. Where did I do? What did I do wrong? This was wrong. This is wrong here. That should be -1 plus 1.
yes.
I copied wrong. I just copied wrong. Okay, so we just have to change all those signs. So let's do a bunch of erasing here.
I got a very interesting case in when I and J equal 50.
Okay, so let me just fix this. This should be minus, minus, minus here. And then everything, all the signs switched because I had the signs backwards. So this is going to be minus, minus, minus. And then all the others are going to be plus. So we'll take this off, 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 off. And then these are all pluses here. And the 2 has a minus in front. So I'm going to just get rid of this. So, see, I didn't make any mistake at all. I completely covered the evidence. Nobody can ever tell I made a mistake. All right.
Dr. Thron.
Okay. All right. So let's see.
Dr. Thron.
Yes.
When I and J equal 50, that 50th spot
Yes.
in the matrix,
Yes.
I found that something interesting happens in the case that it's not 2, it's not -2, it's actually -1.
Yes. Okay. Yeah, you're a spoil sport. That's true. At the very end, it gets screwed up. That's quite true. At the end, it does get screwed up. So that's what makes this a difficult problem. But you're quite right. The last row gets messed up.
And then in BF, it's the exact opposite in the very first location.
Yeah. Yes, that is exactly true. So if you do this problem completely correctly, and you did that from the expressions here?
I did it symbolically, yes.
Yeah, okay. Yeah, well, we can look at what's, see, so I think that with, well, the thing is that here,
I wrote it really weird, but I mean, technically it does work.
so here, well, the thing is you have to be very careful when k is 50, because when k is 50, then some things may not work out. But all right, let's take a look at C then. C. So when you let me just ask you, Trey, when you worked out symbolically, where did it go wrong? Did it go wrong here at the 50, at the limit 50 up here?
So when I did it, and I don't know if like this is a good move or like entirely valid, like it works and it makes sense. But when I did it in that part C part,
Yes.
that second delta,
Yes.
I switched it from delta of k minus 1 comma j to
Yeah. Yes.
delta of k of j plus 1.
Yes. That's well. Kind of.
It doesn't change how it works at all, and it gives the same answer as the before. So I figured it worked. Right?
Well, in fact, you are right. In fact, you are right. But there is a problem when you have to be careful about the limits, because you're actually changing. So what you're saying here, which is very true. So what you're saying here, that's actually a very good move. That's equal to delta k j plus 1.
Yes, that's what I did.
Okay. All right. So that's, and that is still true for k equal 1 to 50. That is still true. So you're saying that when this is 1, this is also 1.
Yeah, for sure.
So that is a very good move, and that's perfectly valid. And you can do the same thing with this. So how would you do with this?
I mean, I did the same.
Very same thing. Yes, that works just fine. Well, okay. Okay. All right. So if you do that, what you're going to get, what you'll get for C, it's getting kind of junky here. But let me see if I can just copy this, because I'm not going to remember it. Here, I'll just copy both C and D if I can. Okay, I think that actually copied pretty well. So here we'd be using, if we're using the components instead. Okay, so we do that. All right, so there's C and there's D. So that gives us, if we do that, then C, let me erase this here because it's, don't have this. Okay, so C would be equal to, C would be equal to minus, so you're doing that replacement, sum k equal 1 to 50. And then this is delta I plus 1k. And then this is going to be delta k j plus 1. And then the other case, you're going to get plus sum k equal 1 to 50. And then this is delta ik and delta k j plus 1.
And then this is where I did a
Okay.
I broke it up into two equations,
Uh-huh.
and the one equation was when I and j do not equal 50,
Okay.
and I said that was equal to, the negative delta of I plus 1 comma j plus 1.
Okay.
And then when it does equal 50, because k can never equal 51, it will never equal 1.
Yes.
So in effect, that is equal to 0.
Yes. Well, that's exactly right. So you do have two cases here. Here you have where k is less than 50. If you have k is less than 50.
No, I and j are less than 50.
No, you're right. Yes, you're right. It's I and j is less than 50. In that case, you're going to have, you'll have delta I plus 1 times delta j. I'm sorry, I should say that. Then you'll have delta I plus 1 j plus 1.
Yeah.
Okay. And that's also, will that also be true if I and j are 0? I mean, I and j are 1. Yes, it'll still be true if I and j are 1. Yes.
Because
And
k will be 2. Yeah.
and then in the other case where I and j is equal to 50, then it's equal to 0 since k is unequal to 51. Now, I don't think you have the same problem here.
No, I did not have the same problem there. So yeah, that was a case with only that section, only section C.
Right.
Section D.
Yeah. Okay. Well, that's very good.
Now that I look at it, I wrote the answer really weird.
But I mean, what you have is very good. So from A and B, what did we have? We had so A plus B plus C plus D. So you now have two cases. You have the case where I and j are less than 50, and you'll also have the case where I and j are equal to 50.
Yeah.
Okay. So, well, I think you have to say I or j is less than 50.
So that's where it's interesting. Because of how it's written originally.
Yes.
It has to be and, because otherwise they'd be 0 anyway.
All right. Well, let's try this. The only exception to your rule is when I and j are 50. Otherwise, it works. So you can write. So the A was delta ij, I believe, right? The A is delta I plus 1j, and the B was minus delta ij. So we have delta.
So I did combine those.
Yeah, you have delta I plus 1j minus delta ij. Well, you can combine them except for one case, right?
Yes, exactly.
So this is actually the same as delta ij. So it's going to be minus delta ij, and then we have plus delta ij plus 1. Now, but there's one term. The 50 is exceptional, right?
Yeah.
So you can just write this. That will take care of it. Well, no, I should say no. I didn't say that right. You have to say delta I50, delta J50, like that.
Yeah, that'll work. That's way better than what I wrote.
So let me write it more clearly. But like I said, that 50 term is very difficult.
Can you just do a three-way? Can you
They don't write it that way because, I mean, you could define something like that, but that would be very specialized. Or you can say that or we can simplify these two together, right? So that would be the same as delta ij minus, I'm sorry, delta I plus 1j minus 2 delta ij plus delta I j plus 1. And then you say plus delta I50 delta J50. But this substitution here, I didn't think of that. That's really very good, the way to deal with it, to make this substitution. That's a very good way to deal with it. Because that will be true for any k and j. That will always be true, that if k minus 1 equals j, then k equals j plus 1. That's a very nice way of doing it. I think that's probably the hardest problem in the whole set. Unless you show me a harder one. So what else should we talk about? I didn't assign this one. Are you still there? Okay, yeah, it's already cut off for a second. All right. Yeah, I'm going to call again. I'm going to call again.
It's up.
Okay. All right, now the two abbreviated notations, this one, let's see. There are two abbreviated notations. Let's see, how can we do this? You basically, you just, for this one, you basically just leave off the upper limit. That's pretty much what it is. You just leave off the upper limit, and then for the other one, you don't even put the sum. So, so
I wasn't sure.
So it says both abbreviated notations. This would just be, I think I can just say it. The first notation would just be sum over ijk, and then you just say aij bgi ckk. That's all you'd have to do. And then for the, actually, if you look at this, the sum over k can be separated out on the C. So you could write this as sum over ij, aij bgi, times sum over k of ckk. You could write it that way also. And then if you use the Einstein notation, it's just going to be aij bgi ckk. That's all you write. And it's very similar here. You would just write, in this case, you would have, you would just write sum over lmn of alm bnl cmn. And then in Einstein notation, you just leave off the summation signs. So does that make sense?
That makes sense.
Notice that these limits never depend on the other variables. Like this p does not depend on the j or on the I. So you don't have to worry about interchanging sums. You only have to worry about interchanging sums if the limit of the sum depends on the other variable. And in this case it doesn't. So I think you also had a question down here on 7.5.17.
Yeah, yes, sir.
Didn't I just define A? I hope I didn't give you B. Did I give you B?
You give us A. Just A.
Okay. All right. So let's see. So remember we talked about invertible functions in the function section. Now the way to show that transpose is invertible is to give an inverse. All right. So for example, if you take, let's just take any old matrix. Let me do this. All right, so here, I guess we go here. All right, so so the question is, so this is 7.5, what's it? 17. So is transpose invertible? All right, now suppose let's do an example. Now of course example is not a proof, but example is how you figure out how to prove things. So let's just do some matrix here, 1, 2, 3, 4, 5, 6, right? Now if I take the transpose of that, I'm going to get what? Not quite. When you transpose, you change the rows to columns and the columns to rows.
Oh, so it's 1, 4.
Yes. Yeah, I mean, the easy way to do it is look at this row, 1, 2, 3, and write it as a column. Look at this row and write it as a column. All right, now, the question is there a way to go back from this matrix back to the original one? Well, let's see if that works. If I take 1, 2, 3, 4, 5, 6, like this, and I take the transpose, so what do I get? Well, I know that rows become columns, right? So that's 1, 4, 2, 5, 3, 6. So yes. All right, so yes, in this case, in this example, it seems that transpose is its own inverse. So what you want to do is you want to prove that transpose is its own inverse. I guess there's no apostrophe there. Sorry. English majors will get on me. Own inverse. And that's the same thing as saying that for any matrix, so I say i.e. for any matrix M transpose will be equal to what?
You can prove that by doing an element by element.
Sure.
That's the best way.
Sure. It may even be in the chapter. Is it in the chapter? No, I don't. I don't see it here. So, not here anyway. But what you want to prove is that matrix transpose transpose. So you could prove it element by element. That would be a good way to do it. So why don't we think about how you would do that?
So, for any matrix M,
Okay.
it would have every element inside would be M of ij.
Okay. Yes, you have Mij. So I guess I can write M is equal to I think, how was I writing that? Something like this.
Yeah, that works.
All right. So then, so that means, well, then you'd have this.
And then the transpose.
Well, what does it say? How does it say it here? And it says M transpose Ij equals AJI. Okay, so we can use that. M transpose Ij is equal to MJI.
Then you just transpose that again.
Yeah, so that's the question. How would you transpose that again?
Just do it.
Well, but what notation are you going to use? M transpose, well, I guess the way you do is M transpose transpose
Yeah. And then bracket.
Ij is equal to M transpose Ji, which is equal to what?
Which is equal
Yeah.
to ij.
Transpose ij.
Well, I mean, yes, if you take the transpose, it flips the indices. So that's it's going to be Mij, and that's the same thing as M. That's the same thing as Mij. So it might be better not to use the little m's at all and just do it with the big M's. I shouldn't write it this way. I should have written it this way. I should have said this. Mij. The ijth entry of M is Mij. Probably better not even to bring the little m into it. But yeah, I think that's the way you would do it, is do it by component.
Run it back and forth.
Okay. Anything else? Let me stop the recording. All right, well, I can do one of them. Ordinarily, I wouldn't do one I assigned, but that's okay. Let's see. So let me go back to, so this is 754. All right, so here we are, and we'll go insert screen clipping 754. I'll go ahead and do, I can do this one, sure. Oh, it's, oops. All right, here.
He's smarter than here.
Okay, let's see. So you got to get this here, move it.
Oh, you'd be surprised. He's listening.
Okay, you know, I can hear. The microphone picks up at a distance. It's quite good at that.
Choosing to ignore you.
Yeah. All right, so this is too small. Okay, here we go. All right, so let's see. So what you want to do is use that formula. The point of this exercise is to kind of give that formula. So let's see. The formula up here was all right, it's this formula here. So let's grab that. Let's see if it's going to work. Okay, yes, okay, move it over. All right, so we're going to use this, and I'll just get rid of this. All right, so let's see how to do this. All right, so let's see. What we want here is, it seems like even the letters are the same, so we just want to plug things in. AIK is going to be 2 to the IK, And bkj is going to be 2 to the minus kj. So in this case, it's going to be, I'll figure out what the limits are later. It's going to be 2 to the ik and 2 to the minus ik, minus kj rather. To the minus kj. You see, I had to change the indices because this is ik and this is ij. So I just replaced the indices like they're supposed to be. And then this is sum from k equals 1 to what is the question.
1 to 20.
And it should be 20 because everything is there. All right, so now it's just a question of algebra. How am I going to simplify this?
You can make it 2ik minus ki kj.
Oh, yeah, you can do that.
And then to take kj.
Okay, so that's equal to sum k equal 1 to 20. Now, can I simplify this?
Yeah, you can do 2k times I minus j.
All right, now, all right, but now look what we have. I and j are 20. I and j are 11. So I equals j equals 11. So what does that give me? K is 1 to 20. Just plug them in. 2 to the what? To the 0. Okay. So that's k equals 1 to 20 of what's 2 to the 0?
1
All right, so what's the answer?
20.
All right. All right, now for part B, I'll just tell you have to use geometric series. You'll have to use geometric series, but it's quite similar. Then the geometric series, I think somebody told me that, let me verify this. Geometric series was in section 3. I think it's quicker just to do this. It says 4. Oh no, it's section 4 actually. Okay, so let's see. Geometric series is not this. Here, all right. Here's the geometric series. All right. Yeah, this should be a 1/2 here. Sorry. Now here is geometric. So this is the sum from 1. This works for 1/2. The sum of 1 plus dot 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 plus 1/2 to the nth power gives you this formula. But this is the general formula. So you should be able to use this to solve that problem.
I guess nice terms where it's all the numbers not actually plugged into the calculator.
Yeah, usually yes. If it's a fraction, you mean like a fraction, right?
Like leaving it as
I typically prefer leaving it as a fraction, yeah. Then I can see, then that saves me the trouble of going to a calculator and figuring out.
and I'll leave it like that.
Yeah, that's fine. Saves you the trouble also.
I will take it.
Okay. All right, so are we good?
I think we're good.
Okay. I'm going to stop the recording.